Okay, I told you that there's a little bit of quantum magic happens when we do this quantum Zeno experiment and this quantum Zeno measurement or non-measurement that resets the wave function, and in the fact that no, literally no wave function is lost when it's reset, is what is the cause of it is the way we calculate probabilities in quantum mechanics. And it's essentially the same way we do in different quantum mechanical settings, different systems, perhaps differently defined angles, but uh, pretty much the same idea there is. So let's see. When I've been speaking about Mach-Zehnder interferometer or any other interferometer, I was cheating a little bit. I told that this is a 50-50 beam splitter. But what it does, it splits the wave function into half. Half here and half here. But the wave function might have negative and complex values. What we want is the probability of something being somewhere. Yes, and in order to do that, we need to square the wave function. And here's where the hidden trick comes. So how you calculate the probability, for example, of, imagine you have a horizontally polarized photon, so 0 degrees polarized photon. What's the probability of success for this photon to pass? Let's look at our bomb setup. Let's say we have a bomb. What's the probability of the photon to pass our setup? Well, it just goes directly through this arm here, and it never touches the bomb, so it's 100% probability for it to pass. If we were to, that's easy, 100% probability. If there's a vertical photon, 90-degree rotation, there's 0% probability. And if we were to plot it, here's the probability of success, i.e. the probability of not hitting the bomb, and here's the angle theta. This is maximum 90 degrees, this is 0 degrees. We would have for 0 degrees 100% probability, for 90 degrees 0% probability. For example, 45 degrees, we would have 1/2 probability. And actually, by calculating it correctly, in quantum mechanics you calculate by taking the cosine square of the angle of the rotation, and that's square root of 2 divided by 2 squared, and that's 2/4, that's 1/2. That's exactly what we would get also quantum mechanically. That's half approximately here, 45 degrees. But now we would assume, our mind sometimes does it, that there's a linear dependence. If we didn't know about the cosine square law, because the probability, we tend to think about it like linearly decreasing for usual things, there's linear law between them. And for example, for angle of 22.5 degrees, we would expect 75% probability, and for angle 67.5 degrees, we would expect 0.25% probability. But when we calculate it quantum mechanically by this formula, and this is actually where all of the many of the cool quantum mechanical things are hidden. This is Bell inequality, this is measurement problem, this is wave function collapse. So all of it is strange in this particular way. We find that for 22.5 degrees we are actually having 0.85% probability of success, and larger than a linear relation would expect. And for 67.5 we find 0.15% probability, so smaller. And overall, this is how our graph looks like. Maybe it can be a little higher like this. This is how our graph looks like. Well, you might say, yes, it's obvious, it's cosine square piece of graph. But actually, when you think about the probability changing in this way, there is no classical way no classical analog how to create such a probability graph. And that's kind of the essence of quantum mechanics, along with interference. That's what happens all the time. That's where quantum weirdness is residing. You get many weird quantum things happening because of this. And quantum Zeno effect is actually one of them. In order to understand why, when we have very, very small changes into the angle of the rotation, why if we reset the wave function back, we don't lose a part of wave function, as long as this reset is small enough. This part of the graph is responsible for it. The way it enters the 100%, not linearly, but in this cosine-ish fashion, is what is responsible for the fact that as long as these rotations are small enough, as long as the time of the evolution you allow system freely to evolve is small enough, and you measure it constantly, so as long as you're fast enough in resetting the wave function, you will be able to get essentially 100% success fidelity for our setup, or 100% like essentially you will be able to hold the quantum system in a particular state without the leakage of wave function in some way. So, and this is kind of the edge until where I can say something about it. It's already is somewhat mathematical, but pretty much the shape of the graph, or the way how we calculate probability in quantum mechanics, is responsible for it. For you, if you're fast enough, you're able to reset your wave function without loss of the wave function. And if you think of something, some interesting way how to interpret or think about it, you definitely should let everybody else know. So this is what I wanted to tell and to have a sort of imaginary dialogue about. I hope you had fun, and it was interesting for you to explore this small example that I've brought up. I like it very much because it has so many layers of interesting things, and you can actually play around with it even more. For example, you can think, okay, if I am able to test a single bomb using a photon, and then I'm left with that photon, I have photon still. Photon doesn't disappear. Perhaps I could test a new bomb, like a second bomb with the same photon, and have like a result of the existence of the two bombs. But now there's four possibilities, like bomb and bomb and bomb, no bomb and bomb, bomb and no bomb, no bomb, no bomb. There is perhaps a way to do that. Why don't you think yourself? How could it be done? Perhaps by, if you don't want to know, then switch off the video, but I'll tell maybe some hints. Perhaps by chaining some like interferometers, or chaining some setups that would test one bomb into a second bomb. And another hint that I will give to you, now there's four exits. Before we had just two exits, so you need to think of a setup that has four possible distinguishable results. So think about the ways how you can inscribe your information about the bombs. If you want to switch off, then there are some more hints. You may think about the setup as a setup like this, and it gets you photon in horizontal or vertical polarization. That's it. You don't have to draw all of the interferometer. You can think about it, but you don't have to draw all of it, and then it will be maybe easier for you to construct the things. So try playing around with it, try to think about it. Perhaps you come up with something. Even not 100% fidelity is fine. Yeah, so let's see how it goes, and good luck. Thank you for attention.